In the last lesson, we were working with just one sample, but in this lesson, we're actually going to compare two different samples. We're going to be talking about independent samples and dependent samples. We'll be talking about using the z-test and also testing proportions and also using the t-test. Now, before we get started talking about two-sample tests, let's just remind you of the five-step process in hypothesis testing. The steps are going to be the same. We're going to be computing different statistics. We're going to be introducing you eventually to the F statistic and the chi-square, and we've used already the z and the t, but how we compute the z and the t are going to be different depending on whether we have one sample or two sample. But the other four steps around it are always going to be the same. First, we're going to state the null and the alternate hypothesis. Remember, the null hypothesis is what's assumed to be true. It's the status quo. The alternate is what you're trying to prove. You're going to select a level of significance, which in most cases is going to be 0.05 or 0.01, but remember, anything from 0.1 and smaller can be a statistically significant level of significance. Then you're going to identify the test statistic. Are you going to be using the t, the z, the f, or the chi-square? And we'll be introducing you to those. Remember, for right now, we use the z if we know the population standard deviation, or if we're doing a proportion, we use the t if we don't know the population standard deviation. Then finally, we're going to formulate the decision rule, which is the critical value. We're going to look up the critical value of the z or the t that we're comparing what we compute to. Then we're going to compute it, and then we're going to make our decision as to whether we reject or do not reject the null hypothesis based on comparing the computed test statistic, the computed f, the computed t, the computed z. We're going to compare that to our critical value. And the general rule is, if what we compute is smaller than the critical value, then we're going to not reject the null hypothesis. Well, here are some reasons that we might want to compare two populations when we're going to be doing a two-sample test. So with the slides that you see here, maybe we're wanting to see if there's a difference between the value of the residential real estate sold by males versus females. Or in a college example, maybe we want to compare the test scores, males versus females. So we're going to be comparing two different samples. All right, as I just said, remember the five steps to hypothesis testing are going to be the same. However, when we actually compute the test statistic, how we do that will be dependent upon what we're actually testing. In this case, we're testing two samples. So this is the formula that we're going to be using for a two-sample comparison of population means when we know the population standard deviation. So in this case, we have x bar 1 minus x bar 2 divided by the square root of the variance of the population 1 divided by the sample size for 1 plus the variance of population 2 divided by the sample size 2. Alright, so here's an example of how we're going to run through a z-test of two samples. So we have a grocery store facility, and they're wanting to see if the self-checkout is faster than the standard checkout. So we have the sample mean of the standard checkout and the sample mean of the U-scan, or the self-checkout. We happen to know the population standard deviation of both of those, and then we have the sample size given to us. So once we have this information, then it's very easy for us to go ahead and compute a z-score. But first, we're going to have to go through all the steps of the hypothesis testing and come up with a critical value so that we can compare what we compute to the critical value to determine whether or not we're going to reject or not reject the null hypothesis. Alright, we're ready to go through the five steps of the hypothesis test. The first step is to state the null and the alternate hypothesis. Now, remember, they're trying to prove to us that we should be using the self-checkout because it's quicker than using the standard checkout. And so the alternate hypothesis is that the standard checkout takes longer than the self-checkout. So the null hypothesis is that no, it doesn't take longer. Essentially, there is no difference, or it isn't longer. So null hypothesis is that standard checkout is not longer. Okay, it's equal to or not longer. And the alternate hypothesis is that standard checkout is longer. Now, we have this level of significance. We're going to use the 0.01. We want only a 1% chance of making a type 1 error. Then we're going to determine the appropriate statistic, and because we know the population standard deviation, we're going to use the z-test. Step 4 is to formulate the decision rule, and that essentially means we're going to look up the critical value, the value that we're going to compare what we compute to. Now, this is a one-tailed test because we're only looking in the one direction because we're trying to prove that it takes longer or greater than. And the significance level is 0.01. So if we were to look that up in the z-table, we would end up with a critical z-value of 2.326. That's what we're going to compare the z-value that we're about to compute to. All right, now we're actually ready to compute the z-value, and remember we use this formula when we're comparing the means of two different samples. We know, remember, the population standard deviation of each of these different populations. So we run through the calculations and we end up with a computed z of 3.13. So now we're going to compare that to our critical value. The critical value that we came up with was 2.33. The result is we're going to reject the null hypothesis because the z-value we computed is greater than the critical value. It's out in the tail. It's in the reject area. If it were smaller than the critical value, we would not reject the null. So we can say with at least a level of significance of 0.01, or in other words, only a 1% chance of being wrong, that it appears the standard checkout method is longer. So therefore we could say probably the U-scan method is a little bit faster, at least according to the sample that we've taken here. All right, now we need to explore how to do a two-sample test of proportions. Now remember, proportion is a ratio, so some things that you might be comparing is, is there a difference in the proportion of male students versus female students who pass the statistics class final? Is there a difference between the proportion of workers that call in sick at one plant versus another? Again, we're looking at a proportion, we're looking at a yes-no kind of thing, pass or fail, afraid of flying, not afraid of flying, yes-no kinds of things. Again, we're looking at a proportion. So the 5-step test of hypothesis will be the same, but we're going to use a different formula to actually compute our z-value. As we get ready to compute our z for two-sample proportion tests, we're going to introduce you to the pooled proportion. And you can look at this formula and you can actually see it's pretty simple. We're just going to have the number of yeses for x1 and the number of yeses for x2 divided by the total in both of them. So instead of just having each proportion, we're going to pool the proportions together, and that will become vital in computing the z that you'll see on the next slide here. Here you see the formula that we use to compute the z of a two-sample test of proportions. You can see, as the slide shows you there in the little red circle there, that we have to use the pooled proportion. So we compute that first. After we've computed the pooled proportion, you can see the formula is relatively simple. Proportion for sample 1 minus the proportion for sample 2 divided by the square root, and again use the pooled proportion times 1 minus, and you can read the formula there for yourself. And very, very easy to set this up in Excel or even a calculator. Okay, now that we've introduced you to the formula, let's go ahead and run through an example. So in this example, the perfume company is wanting to see whether younger women or older women prefer this particular perfume that they're testing. And so, again, it's a proportion. Yes, they do, or no, they don't. So how many women, young women, preferred over how many young women were sampled, how many older women preferred it over how many older women were sampled. So again, we're going to see if there's a difference in the proportions. Right, now that we've set up the scenario, we're back to the 5-step hypothesis testing procedure. The 5 steps are always going to be there. The only thing that's going to be different, as I said many times before, is how we actually compute the test statistic. So, step 1 is to state the null and the alternate. So in this case, we're assuming, okay, there is a difference. Alright, so there is a difference versus there isn't a difference. So the null hypothesis is that there is no difference whatsoever between the younger women proportion and the older women proportion. And the alternate, or what we're trying to prove, is that there is a difference. That we maybe want to market this either to the older women or the younger women. We set a level of significance of 0.05, so in this case we need then to formulate the decision rule or establish the critical value. This is a two-tailed test, remember, because we're assuming there is no difference. We're trying to prove that there is a difference. And so in this case, we have 0.025 on either end. So our critical value for z is 1.96. And you can see in the slide a couple of Excel functions that you can use to also compute the critical values. All right, the next step is to actually compute the z statistic. So we did the sample and we found the proportions. For the proportion 1, we found 19 of 100 preferred it. And on proportion 2, 62 over 200. So then we pool the proportion together, and you can see that the pool proportion is 19 plus 62 divided by 100 plus 200. Again, we just take them all together. We end up with the pooled proportion of 0.27. We use that along with the individual proportions for sample 1 and sample 2. We end up then with a computed z of negative 2.21. Alright, then we go ahead and compare the z value that we computed, negative 2.21, to our critical value, and we can see that it is more negative, or it falls outside the do not reject area. So in this case, we would reject the null hypothesis. Alright, we've talked about doing two sample tests. When we know the population standard deviation, we're going to use the z, and when we're dealing with proportions, we're going to use the z. However, if we are working with two samples and we do not know the population standard deviations, we're going to use the t. So the 5-step hypothesis testing procedure is going to be the same, but this time we're going to use a different formula. We're going to use the t statistic and a formula to compute the t with two samples. All right, here we have the computation for a t when we're working with two samples. And you can see that we have to first pool the sample standard deviations, and we can do that pretty easily with Excel. Then once we have the pooled standard sample deviations, then we can go ahead and compute the t. Now we'll step through an example here, but quite honestly, it really makes a lot more sense just to use Excel. Excel's data analysis tool will do this for us very quickly, very easily, but we'll go ahead and step through it longhand and then show you how to do it in Excel as well. Alright, so here's our example. So the lawnmower manufacturer has two different ways of assembling, and we're taking the measurements of how long it takes to assemble the lawnmower using this one method versus the other, and we're going to try to see, is there a difference between these two methods. Alright, here we go. 5-step hypothesis testing procedure. State the null and the alternate. The null is there is no difference between these two procedures, and the alternate is there is a difference. So this makes this a two-tail test because we can go either direction. It might be slower, it might be faster, but there is a difference. We're going to use a significance level of 0.1. We're then going to use the t-test because we do not know the population standard deviations. Alright, then we're going to have to figure out the critical value, or state the decision rule as the proper terminology says. It's a two-tail test. The significance level was 0.1. That means we're going to have 5% on each tail. We come up with a critical value of negative 1.833 and positive 1.833. Well, here's how we came up with that critical value of 1.833. We have the degrees of freedom, which are n1 plus n2 minus 2. Remember, there were 5 in the first sample and 6 in the other, and then we have 2 samples, so that's why we subtract 2. Then after we have the degrees of freedom, we find the level of significance column. This is a two-tail, so we're looking at the 0.1 level of significance, two-tail, degrees of freedom 9. We end up with that critical value of 1.833. Alright, here's how we would compute this manually if we wanted to. The first step is to compute the means. So the mean of sample 1 is 4. As we can see, 20 divided by 5 is 4. The mean of sample 2 is 5. Okay, 30 divided by 6 is 5. Then, of course, we're going to compute the standard deviation. Now, I just want to remind you that the standard deviation, if you're computing it manually, is simply the sum of the squared differences between each value and the mean. And then we're going to divide that by n minus 1 because this is a sample. Alright, so once we have the standard deviation for each sample, then we can go ahead and compute the pooled sample standard deviation. You see the formula down at the bottom is simply the sample size of n1 minus 1 times the variance of the sample. Remember, the variance is the standard deviation squared. So once we've got this pooled sample standard deviation, then we can go ahead and compute the t. So again, computing the t-score manually, once I have the pooled sample standard deviations, I can go ahead and compute the t. We have x bar 1 minus x bar 2 divided by the square root of the pooled sample standard deviations divided times 1 over the sample size of 1 plus 1 divided by the sample size of 2. Anyway, once we've done that longhand, we end up with a t-score of negative 0.662. Now, we could look very, very quickly and see that no, that is not more negative or more positive than 1.833. So in this case, this is in the do not reject area. So we are not going to reject the null hypothesis, and we are going to conclude that there is no difference between the assembly methods. All right, now you see the real reason I kind of rushed over that formula in computing that t-score manually for two samples. It's very, very easy to do this in Excel's data analysis feature. You just select the t-test to sample assuming equal variance, and you see the result here in the slide. You can see that it computes the t-stat for us as well as the pooled variance, and using Excel also gives you the critical values of one tail and two tail. Remember, this is a one tail test, so it shows us there that the critical value was 1.833. You'll also notice that the result of this t-test, it also gives you the p-value. Now, we haven't talked about the p-value too much here, but Excel is very easy to compute the p-value with several functions that it has, but the p-value allows you to compare the stat that you computed, the probability of making a type 1 error, versus what you were after. Remember, we wanted a 0.1 significance level or only a 10% chance of making a type 1 error. We've ended up with a p-value here of 0.525. So this is telling us there's more than a 50% chance of making a type 1 error. So definitely we do not want to assume that our alternate hypothesis is correct. We're not going to reject the null. Well, when we're comparing the means of two samples, we need to also understand whether or not we're talking about dependent or independent samples. In the instances so far, we've been using independent samples, which means they're not related to each other. A dependent sample is essentially when we're looking at the same sample, we're doing kind of a before and after study. Maybe we're looking at a sample before they've taken the stats class and after they've taken the stats class, and then we're giving them the same test and see, did they do better afterwards. So we'll go ahead and run through an example of a dependent sample, and I'll just tell you right off the bat that this is something, once again, you want to do in Excel if you can, using the data analysis feature. It's much easier to do it in Excel than to do it manually. Alright, so here's the scenario we're going to use for dependent samples. So there's a sample of 10 houses that have been appraised, and they've been appraised by two different companies, and we're going to try to see, is there a difference between the one company and the other company appraising the same house. We're going to be using the 0.05 significance level. Alright, this computation really isn't too bad here. To compute the t of dependent samples, we're simply going to first take the mean of the differences, and we're going to divide that by the standard deviation of the differences, which is also divided by the square root of n, the number of pairs. We'll go ahead and compute that manually just to show you how it works, and then we'll also show you how to do it in Excel. So once again, we go through the same 5-step process of testing hypothesis. So we state the null and the alternate. The null hypothesis is there is no difference between the two companies. The alternate is that there is a difference. Again, it could be one company does it less, lower price, or higher price, but again, just a difference. 0.05 significance level, and then we're going to find the critical value here in the next step. Our degrees of freedom, because these are dependent samples, there's essentially only one sample, so it's n minus 1. So our degrees of freedom is 9 because there were 10 houses that we were looking at. We're looking at the 0.05 significance level for a two-tailed test, and so therefore our critical value comes out to be 2.262. Okay, so here's how we actually compute the t involving paired dependent sample. We first come up with the mean of the differences. which in this case is 4.6. We then come up with a standard deviation of the differences, which is 4.402. Finally, then we can go ahead and compute the t. We come up with a t of 3.305. That is greater than the critical value that we came up with, and so therefore we are going to reject the null hypothesis and assume there is a difference between these two appraisal companies. Now, as you can see with this slide, there is also an Excel data analysis test that will allow you to do this. This is the t-test 2-sample for means, and it works just like the other one. You just put the input range, the output range, your alpha level, level of significance, and an output range, and in this case you can see that it does indeed compute the t-stat, and it also gives you the critical values and also the p value.